Now, let me start with the idea of autoencoding here. So what is the autoencoding? So the thing that is happening right now is that what you have one Q, which can start from one data sample and give you some distribution of the latent, right? Forget about the concept of distribution. It takes the data, it gives you latent, right? And then you have the latent. You pass this latent through the generator, you're going to get a data sample, right? So this is getting from data space to latent space and then back from latent space to data space, right? Which is what you do always in autoencoding. You encode data to latent and then you decode it back from latent to data, right? Now, I do not expect you that you immediately see the connection of this, what we are doing here, to the conventional autoencoders. We're going to see it at the very end of this section, okay? Once you understood all the details. But the key point here is that we essentially are doing a sort of autoencoding, right? And the decoding part is already clear to you. The decoding part is what we used to call it probabilistic generation, right? That generator is your decoder, right? Because what it does, it's going to get one latent sample Z, and then it's going to sample one data sample for you, right? So it gets you from the latent space into the data space, right? This is the decoder. And the decoder is simply consists of one neural network, one deep model G theta is going to get Z, one latent sample, in the m-dimensional space and returns one value. And that value is essentially the mean value of the distribution that you want, right? And in addition to that mean value, it's going to have one Gaussian sampler, right? Which looks at this mean value and sample with that mean value, right? Which is essentially sampling one IID Gaussian adding up to the mean value, right? This is your decoder. This is the way that you get from one latent sample into the data sample, right? Now, one thing else that we need here in this autoencoder is the encoder, right? The encoder is the guy who is taking us from X to Z, right? And this is essentially the Q model, right? Because Q is the one which is looking at the X value and then gives you the distribution of the latent. Everybody's clear? Okay, so Q is essentially your encoder, because what does Q do for you? It's going to look at one X, it's going to take one X as input, and it's going to return you the distribution of Z over that X, right? It's going to tell you that if your data sample is this one, your latent representation is somehow distributed in this part of the latent space, right? This is the distribution that I can tell you about your latent. It's not going to be that point. Most likely it's going to be somewhere around these points, right? This is the thing that Q is telling you right now, right? Everybody's clear? Okay, so this Q is the encoder. It's going to get X, it's going to take you to latent. Now it's going to complete the whole autoencoding architecture. From data to latent, from latent back to data, right? So it is indeed one autoencoder, but it is not yet the kind of conventional computational autoencoder you used to think of, which gets the exact sample. It just finds the exact latent representation and takes you back to exactly the same sample, right? This was the one which you use, for instance, if you want to do denoising, right? If you want to just do compression. That is the way you think of autoencoders. But once we just write down all the ELBO everything, you're going to see that those things you used to do in deep learning are essentially a special case of what we're doing here. So it's a more general case because we're talking about distributions. We're not talking about exact samples. OK, so this is the encoder that we want. Now, the encoder that we want, it needs to have one extra condition as compared to the classic distribution that we have. Like, if I say that, the first constraint that I have written here is that this QW Z given X is a distribution on Z, right? So when it's a distribution on Z, what do you conclude? What does it mean? What should it be? What kind of properties Q needs to have to be a distribution? if Q, Z given X is a distribution on Z, what kind of properties does it have? It sums up to 1, so if I integrate it over Z, it's going to be 1. What else? Non-negative, exactly. So Q, Z given X, it should not be negative, right? These are the constraints that any distribution would have, right? So if I just have these two constraints, it's okay. But I need one extra constraint here. And the extra constraint is that I want this guy to approximate, when it's marginalized over my data, the latent distribution, right? Because what I do, what I'm trying to do with this Q, I am trying to approximate the posterior distribution, right? So this Q guy, this QW, is trying to approximate P of Z given X. So if I had really PZ given X, and I multiply it with data distribution and marginalize it over all data, it's going to be exactly the latent distribution, right? So I need that this Q distribution also be able to do that, right? Everybody's clear? Because my latent distribution, PZ, is fixed, right? From the very beginning, I said that my Z, my latent variable, is marginally Gaussian, right? Why? Because it's easier for me to sample from Gaussian when I want to generate, right? So I impose this constraint on my Z value, my latent sample to be Gaussian. Zero mean unit variance, right? Now, when I learn Q, it should be able to somehow marginalize to a Gaussian distribution. Everybody's clear? Question on that? No question? So one thing here that you should pay attention to is that what I say here, it does not mean that for every single W this should happen, right? It means that there should be one W at least that have this property, right? At least one W which could do this, right? Because if there is no W, there is no parameter on my model that is able to make one Q distribution that is marginalizing to my latent prior, this means that this model is not able to capture what I want, right? So it would never be able to approximate the posterior distribution of the latent, right? So you don't confuse yourself that I mean that for every W this should happen. This is not the case, of course. This is going to be a very big, this is going to shrink my model significantly. I essentially have no model anymore. This simply means that, this could be any W, but there should be at least one W which has this property. Because if I have no W with this property, this means that for no W, this Q is going to be approximately the posterior. This means that this Q is not a good Q for me to use when I am doing variational inference. Everybody's clear? Question? No question? Cool. So if you got no question, let me just go ahead and design this Q distribution. First of all, do you have any suggestion for Q distribution? No suggestion? Okay, take a look at this slide. Hopefully by the end of this slide you have some suggestion for me. So let me write down the extra constraint that I have. Oh, I thought this is in the next slide. Okay, so do you remember this result last time? Huh? So when we have a Gaussian mixture distribution, this Gaussian mixture is capable of doing pretty much, or mimicking pretty much any distribution, right? We talked about this before, right? Now, what do we want? We have this Q, right? And what we need to have is that when I marginalize this Q over data distribution P data, this is going to be this P hat, right? And this P hat should be a good approximator of the latent prior, which is Gaussian with zero mean and unit variance, right? Now, what do you think that is a good choice of Q? How can I design Q? Gaussian, great. I need to make Gaussian with a mean and variance, which is depending on x, right? If I do that, then p hat is going to be a Gaussian mixture. And since it's a Gaussian mixture, it's able to mimic most of distributions, including the zero mean unit variance Gaussian, right? So, in other words, if I set this Q distribution to be one normal distribution with mean and covariance matrix, both of them computed for the given x, right? This is a Gaussian distribution marginally. Given x is a Gaussian distribution, right? Now, when I marginalize it over x, this is going to give me p hat, right? And that p hat is essentially the Gaussian mixture distribution, right? Exactly like what we did in the generator, right? And we said that this Gaussian mixture is able to mimic most of distributions, right? If we have a very deep model, those mean value and covariance are given with very deep neural networks, this is going to give me a very good approximation of most distribution that I can think of, right? Including the particular prior distribution that I am looking at. Clear? So then given that, this choice is quite a good choice, right? And it's a kind of easy choice as well, because this is simply a Gaussian distribution. I can always realize it, right? So I just need to know the mean and covariance, and then there is always a very simple procedure to sample from that distribution, right? It's not a kind of weird unknown distribution that I have to use, for instance, Langevin or Gibbs sampling, right? So, moral of the story here, the best distribution that I can do is to just put it to be Gaussian with a mean value and covariance matrix, which are learned from the given data sample x, right? That is the best distribution that I can think of. Easy and at the same time quiet, universal, right? So, moral of the story, for the encoding, I am going to just use one, again, Gaussian, conditional Gaussian distribution. And this conditional Gaussian distribution is going to consist of two neural networks, essentially. One neural network, which is computing the mean value, right? It's going to get any data sample in d-dimensional space. It's going to give me one m-dimensional mean value, right? Because I'm getting from the data space into the latent space, right? So this is the mean value network, and I have a covariance network. This covariance network is going to get one particular data point in d-dimension, and it's going to give me a covariance matrix for the latent space. What is the dimension of the covariance matrix there? So if you have one z, z is going to be m-dimensional, right? If you think of it as a random variable, a random vector, what is the covariance matrix of this random vector? M by m, right? So I need to just return one m by m matrix. So this network should give me one m by m matrix, which is going to be the covariance matrix. Everybody's clear? So I need this mean value and covariance matrix. And then once I have it, I can just sample from a Gaussian with that mean value and covariance matrix. Everybody's cool? Now, if a matrix is a covariance matrix, what kind of property should it have? Sorry? Symmetric, right? But what else? Yes, go ahead. Positive definite, positive semi-definite, right? It could have eigenvalues 0, but it cannot have negative eigenvalues, right? So one covariance matrix is always positive semi-definite, right? So it means that your network, the second network that you have here, whatever you design, you should make sure that this is a positive semi-definite output always, right? Because you cannot have a negative definite or non-definite matrix as a covariance matrix, right? So this is not a complicated thing. We're going to do it right now, okay? So no worries about that. Now, once you have these two networks, then essentially you just need one Gaussian sampler, right? You're going to give your particular x to these two networks to get the mean and covariance, and now you have a Gaussian distribution. You're going to sample from that distribution, right? And as I told you, this distribution is quite easy to realize, right? You don't really need to go ahead and do complicated, algorithms like Gibbs sampling or so. You essentially need to get this x. You pass it through the two neural networks that you have. Then you're going to have the mean value and covariance matrix. Now you're going to get this covariance matrix. You multiply it in a right way, of course, to one IID Gaussian of the same dimension, right? This is going to make that IID Gaussian to be zero mean with covariance matrix sigma, right? Then you're going to add it up to the mean value you computed, right? And now this is going to be one Gaussian variable with mean eta and covariance sigma. Everybody's clear? You got what I did here? If not, you can ask. If I have one random variable, z, okay? Say epsilon. Epsilon is normal with mean 0 and variance 1, okay? If I multiply this epsilon with the square root of sigma squared, what is the distribution of this guy? It's going to be normal, square root of sigma times epsilon. Sorry. What is the distribution of this guy? It's going to be normal. What is the mean value? It's still 0 because you have this one, you just scaled it, right? 0. What is the variance? It's going to be sigma squared, right? Because you have multiply epsilon with sigma, the square root of sigma squared, right? And then the variance is going to be scaled by the square of that coefficient, right? So it's going to be sigma squared, right? Now, what if I add eta to this guy? What's going to happen? Only the mean is going to change, right? The variance is not going to change. So this is going to be eta, right? And this is what you want, right? So you don't really need to do anything complex to generate such a z value. So this is the z that you want, right? So you don't really need to do anything complex. You just sample this guy and do this simple linear procedure till you get into the distribution that you want, right? This is what I'm trying to tell you here. So you have an IID zero mean unit variance Gaussian sample, and then you just process it according to the covariance matrix and the mean value to get the exact sample that you want. That is quite easy. I mean, in the worst case, it's going to be cubic complexity because you need to, for instance, decompose sigma, which we are not going to do, actually. But in the worst case, this is going to be much, much, much simpler as compared to Langevin or anything else, right? Questions? Now, this guy that you see is your encoder. Everybody's on the same page, right? So you're not getting lost, right? Because you don't interact with me anymore, so it's a bit. Do you want a 5 minutes break? You just refresh and then we continue? Yeah? Okay, let me see if I have anything. Yeah, I'm going to talk about it later, okay? So everybody's cool? This is the encoder that we have, as I told you. So now we have essentially a clear picture of the encoder and decoder. So the encoder is going to start from data. It's going to do 2 computations by 2 neural networks. Then it's going to sample from a Gaussian distribution. This is your latent. Now if you have the latent, you're going to do the same thing by the decoder, right? So you're going to get the latent. You do one computation, which is essentially the mean value. And then again, you sample from a Gaussian, right? This is the decoder. Now, a few things regarding this encoder and decoder architecture that we have here, because it might be a question of you. One of them is that how can I make sure that this guy is positive semi-definite, right? And if you want to make sure, this is not a very hard thing. You just simply need to put it to be a diagonal matrix with all diagonal values to be non-negative, right? So this is what we do in practice. So in practice, we don't really learn the complete matrix sigma. In practice, we just learn m different non-negative values, essentially positive values, right? So you're going to have m different positive values. You think of them to be variance of every single dimension. And then your Q distribution can be simply written in this form, right? So look at it here. Every single term that you have here is the z. This is one of the dimensions in your latent, right? Zi is one of the dimensions in your latent. So your z vector, this latent variable, is z1, z2 till zn, right? So every single of them subtracted from its corresponding mean value, so eta I squared divided by 2 times sigma squared, this is the corresponding variance in this matrix, sigma squared of the dimension I, right? So you're going to add all of them together, and this is the coefficient that show up based on the Gaussian distribution term, right? Everybody's cool, right? Now, one thing about this here is that this is quite simple to realize, right? So you can simply have one neural network. That neural network takes one x, going to give you m values. And if you want to keep these m values non-negative, you just need to have your last activation layer to be some function which is giving you always non-negative values, right? You can square everything in the very last layer, right? This is going to be a non-negative variance. So this is a quite simple thing. You're going to start from d-dimensional space. You end up with m-dimensional positive space, right? This is not a hard thing to do by any neural network. So that's easy. This kind of modeling has also a bunch of other properties. One of them is that, obviously it's going to keep the covariance always positive semi-definite. Positive definite indeed, actually, because we keep those sigma values non-negative, positive, not only non-negative. This is one thing. But the other thing is that it's going to give me a very simple way to sample from that distribution, right? Because when I have this expression here, this means that every single dimension in Z space is independent. The only difference is that they have different variances, right? And then you can do exactly the way that I did here. Instead of having sigma only, you're going to have sigma I, right? For every dimension, you're going to get the corresponding I here, corresponding mean and corresponding variance, and then you do the same kind of sampling, right? So this is easier to sample as compared to have a general sigma matrix. Because if you have a general sigma matrix, in this diagram I showed you, before you do the multiplication, you need to compute SVD, singular value decomposition. This could be cubic complex. But if you have a diagonal matrix, then that is easy. You just take the square root of all diagonal values and then you multiply them, right? So that is not complex anymore. And this is one of the key reasons that we stick to this kind of architecture. We don't want a computational complexity, right? Okay? So this is the classical one. Yes?
But does this reduce the degree of freedom of that?
Yes, but the level of freedom that we get is enough, actually. I'm being generous because in many very high quality applications, we do this. But in some basic application, we actually don't even consider different sigma values for different dimensions. We just consider one single sigma for all the dimensions. So you again assume that the covariance is sigma squared times identity matrix, right? And you learn just one single value. That's sometimes enough. Yeah? But the level of complexity that you're going to impose if you think of a general sigma is higher than you can tolerate by computation resources. So we don't do that. Questions? Everybody's clear? Okay, so this is one thing regarding sigma. So at the end of the day, this sigma is just a diagonal matrix, m different variances. That is quite easy. The other thing is regarding the difference between encoding and decoding. But let me first just summarize everything in this diagram. So the variational autoencoder is essentially this autoencoding architecture. And here, the encoder Q is essentially one Gaussian sampler whose mean and covariance are learned from data X. So this is going to give me a distribution in Z. And this decoder is, again, a Gaussian sampler. And that Gaussian sampler mean value is just learned from Z again, right? So these are distributions, that's right. But at the end of the day, inside them, there are just simple neural networks, right? Which are learning mean and variances, right? So it's not something very weird as we had, for example, in energy-based models, right? So you're not really learning the exact distribution. You're just learning mean and variances, and then you use the universality of this kind of Gaussian mixture to mimic the data distribution. Okay, so this is a variational autoencoder in general. One thing that you should pay attention here is that in this model, which part is the generator? If I want to generate with this architecture, what should I do? Say I do the training. I'm over with all training. How do you generate from this? You're going to sample Z, right? You pass it through generator, the decoder. You're going to get the output, right? So if you are only looking into generation, after doing the training, you can throw away encoder, right? So the encoder is pretty much doing the same thing that discriminator was doing in GAN, right? So in GAN, we trained generator and discriminator together. But discriminator was there because we needed that guy to get some gradient for generator, right? To be able to train it. Once we train it, we don't need it. This is, again, the same thing here. So we need this encoder. Encoder is getting into our problem, into our modeling through variational inference, right? Correct? So this encoder is essentially coming here to help us compute some gradient for maximizing likelihood, right? So it's a helper for us. But as compared to GAN, it has one extra property. And that extra property is that it's going to look at one data sample and it's giving us the latent representation, right? So the discriminator in GAN was doing pretty much nothing, right? So if we do the training at the end of the day, it was not something that we can use for any other purpose, right? But here we can say that if we want, for example, to know the latent representation of one data, then we can use the encoder, right? So it's not totally meaningless or useless after the training. So it's not just helping. It's also doing something which might be useful for other applications, right? But if we are only focused on generation, this guy is the same thing as the discriminator, right? It's only there because we need it to be there to be able to train our generator, right? If it's not there, we cannot do variational inference, and so we cannot maximize the likelihood, right? Everybody's cool? So for training, we need the encoder. After training, we don't need it, right? After training, we again do the same generation. You just sample latent, pass it through the decoder, right? Great. So one thing that you might ask me here is that when I'm doing encoding, first of all, for encoding, decoding, if we think about a general variational autoencoder, are we always supposed to consider those conditional distribution to be exactly Gaussian? Of course not. This is not a must. If you are like having some idea, you can go ahead and do it. You can have more complicated distributions. There are actually papers out there where people try to, for example, consider those conditional distribution with some simple energy-based models or so, right? But the key point here is that given the universality that we have for Gaussians, they are good enough. Yeah? So we don't really need to panic about like we are totally suboptimal. This is one thing. And the other thing is that this Gaussian distribution is perfect when it comes to sampling, right? And we really want to use them later for generation. So, even when we are doing the training, we need to sample from them, right? So this is important to always work with easy to sample distribution. Gaussian is perfect in that sense. So this is, I would say, like the 99.9% of the convention that you always work with Gaussian, but this is not a must, right? So you can have, I mean, whatever we have done here, if you put any other distribution instead of Gaussian distribution as the conditional distribution in the encoder and decoder, it's going to work, theoretically, right? How practical that is, yeah, it depends on your design, right? So this is one point. The other point that you might ask me is that when I am doing encoding, I am learning both mean and covariance, right? When I am doing decoding, I'm only learning mean. I'm not learning covariance. Again, this is not a must. You can also learn the covariance at the decoder. But this is not a common thing in practice. The main reason is that if you put the covariance to be learned at the decoder, when you are doing training, you're going to get into a bit of numerical challenges, right? You can have a kind of, dummy solution to your optimization. When you are just training your model, it might be the case that instead of pushing your model to somehow generate right data, it's going to just somehow make the variance of the decoder infinite. And this is not something that you want. Now, I don't expect you to see it immediately. This is why I did not put it in any formulation here. But I'm going to give you one very simple example in next assignment. And you're going to practice that. You're going to see that there are some obvious dummy solutions to the maximum likelihood underlying maximum likelihood problem, where you can get your maximum likelihood, your likelihood very large, but at the same time you're still not learning really anything, right? You just push the variance of your decoder to infinity. Because of that, we're not interested in that. It doesn't mean that if you do this, you're going to always fail. But numerically, you're going to have harder time, right? So this is why we don't do it. And in practice, it's not really needed. So those few notes. And I hope that now everything is clear. Gaussian encoder, Gaussian decoder. And that's it. We need to just do maximum likelihood on that using variational inference. OK? Now, any question? No question. So if you've got no question, let's just put all of those Gaussian things inside the ELBO term, and we try to find out exactly what is the term that we need to optimize when we want to do the training. And that's going to be the end of variational autoencoding.